All right, today we are diving deep into what I think is MySQL's most powerful secret weapon, the InnoDB Buffer Pool. Seriously, it's the single most important component for performance, and once you understand it, you'll see your database in a whole new light.
So, have you ever run into this? You fire off one query and boom, the result is back instantly. Then you run another one that seems pretty similar and you're just waiting. It's a super common thing, and the answer, almost every single time, comes down to one simple thing: where the database is getting its data from.
And that's because there's this absolutely massive speed gap in every computer. When you access data that's already in memory, in RAM, we're talking nanoseconds. But if you have to go fetch that same data from a disk, even a super fast modern SSD, you're now talking milliseconds. Now, I know nanoseconds and milliseconds both sound tiny, but on a computer's timescale, that is an eternity.
Just how big of a difference are we talking? Well, it can be up to 1,000 times slower. To put that in human terms, that's like the difference between waiting 1 second for something versus waiting more than 15 minutes. That gap, that 1000x problem, is pretty much the one single thing that every database engine is designed to overcome.
So here's our game plan. First, we're going to really dig into that 1000x performance problem. Then, we'll see how caching is the clear solution for reading data. After that, we'll look at how InnoDB protects that precious cached data. Then, we'll uncover this really cool concept, the art of writing lazily. And finally, we'll turn all this theory into stuff you can actually go and do.
Let's get right into it. Part 1, the 1000x problem. We're going to see exactly how InnoDB is engineered to bridge that huge divide between super-fast memory and, well, comparatively slow storage.
And this right here, this is the hero of our story, the InnoDB Buffer Pool. At its heart, it's really just a big chunk of RAM set aside to be a cache. Its one and only job is to keep copies of your most used data and index pages in memory so MySQL can avoid making that painfully slow trip to the disk as much as possible.
So that brings us to part 2, caching, the obvious solution. Let's look at how the buffer pool totally optimizes the most common thing you do with a database, just reading data.
Okay, so whenever a query comes in, it goes on one of two journeys. First, InnoDB checks the buffer pool. If the data is right there in RAM, what we call a cache hit, bam, it's returned in microseconds. Super, super fast. But if the data is not there, a cache miss, InnoDB has no choice but to go all the way out to the disk to get it, and that takes milliseconds. That's the difference between instant and not so instant.
So caching seems like the perfect fix, right? Well, almost. What happens when one big, clumsy query comes along and threatens to mess it all up for everyone else? This is what we call cache pollution, and it's a real problem.
Just imagine this. You have a big weekly report that has to scan an entire 20-gigabyte table. If all those thousands of cold pages, data you only look at once a week, get loaded into your buffer pool, they could kick out all the hot data, the stuff your users need every second. Suddenly, your whole application grinds to a halt.
A simple, kind of naive cache would get completely wrecked by that big scan. All your important hot data just gets flushed out. But InnoDB is way, way smarter than that. It uses a special modified algorithm that basically quarantines the data from that big scan, leaving all your critical hot data safe and sound.
So how does it pull this off? It's actually brilliant. The buffer pool isn't just one long list. It's split into two sections. Think of the young sublist, which is about 2/3 of the pool, as the VIP section. This is for the truly hot, frequently used data. Now, new pages that get read from disk, like from our giant table scan, they don't go into the VIP section. They have to start in the old sublist, and the only way to get promoted into the young list is if they get accessed again. The pages from our big scan, they're never touched again, so they just live and die in that old list, never bothering the really important data in the young list. It's so clever.
All right, we've talked a ton about reads, but what about writes, inserts, updates, deletes? Turns out InnoDB has some equally cool tricks to avoid hitting the slow disk when you're changing data. It's all about being lazy in a good way.
And it all starts with this idea of a dirty page. See, when you run an update, InnoDB doesn't write to the disk. It changes the data in the buffer pool, in memory. And at that exact moment, the copy in RAM is newer than the copy on disk. So we call that page in memory dirty. The key here is that InnoDB doesn't rush to write it to disk right away. It waits.
This lazy approach is made even more powerful by something called the change buffer. You can think of it as a cache inside the cache. It's a special area for handling updates to secondary indexes. If an update needs to change an index, but that index page isn't in the buffer pool, InnoDB doesn't bother reading it from disk. No way. Instead, it just scribbles a quick note in the change buffer, like a little to-do list, saying, hey, update this later.
And the performance impact of this is just staggering. Without the change buffer, a single insert on a table with 5 indexes could mean 5 separate, really slow disk reads just to update them all. But with the change buffer, that same insert becomes 5 super fast in-memory notes. All the real disk work gets saved up and done later in a much more efficient batch. It's a total game changer for write-heavy workloads.
So you're probably wondering, if it's not writing to disk immediately, when does this data actually get saved safely? Well, that happens through a process called fuzzy checkpointing. As those dirty pages build up in memory, there are background threads that are always working, gently flushing the oldest changes down to the disk. It's this continuous, low and slow process. The database never has to slam on the brakes and save everything at once. That would be a sharp checkpoint, and it would freeze everything. This fuzzy approach is what gives you that smooth, consistent high performance.
Okay, final section. We've gone through a lot of theory. Now let's turn that knowledge into action. What are the key things you need to watch to make sure your buffer pool is a finely tuned engine and not a bottleneck?
But first, let me be absolutely clear about how important this is. An undersized buffer pool is, without question, the #1 performance killer in MySQL. If you only get one single thing right in your entire database configuration, make it this one.
Here are the 3 vital signs you need to keep an eye on. First, the hit rate. This answers the question, is my cache big enough? You want this number to be above 99%, ideally higher. Second, the percentage of dirty pages. This tells you, can my disks keep up with all the changes I'm making? You want this to be a low and stable number. If it's climbing, you have a problem. And third, checkpoint age. This basically tells you if you have enough breathing room for big spikes and writes. You want this to be far away from its maximum size.
So in the end, the buffer pool isn't just some simple cache. It's really the heart of your database's performance. It's this incredibly sophisticated system that intelligently handles both reads and writes, all to beat that fundamental 1000x speed gap between memory and disk. And that leaves you with one really important question to ask about your own systems. Is your buffer pool a high-performance engine, or is it an accidental bottleneck?